Good afternoon to those in UK. Good evening to those following from India. It gives me immense pleasure to welcome you to yet another joint event with TAIym. I would also like to thank Dr. Cosimo for agreeing to share his experience and knowledge with us today. And of course, TAIym for carrying forward our collaborative endeavors. Before handing over to Sandeep, I would like to highlight that the BTS YouTube channel contains a repository of previously recorded lectures. Feel free to browse through them. And in a similar vein, please subscribe to the channel and press the bell icon to get a live stream notification. So on that note, it's over to you, Sandeep.
Greetings, everyone, good evening, everyone who has joined from India, and good afternoon for everyone who has joined in UK, and my sincere greetings to everybody who is not from India or UK but joining from different parts of the world. It's amazing how we from UK, from India, and from Spain are coming together to make this webinar possible. And we have a special person, Dr. Cosimo, with us today to deliver a talk to us. He's currently working as team leader for underground department of Ayesa. He's based in Madrid, Spain, and he is also assistant professor, and he's focusing his research on the real behavior of joints between segments of TBM lining. He has worked in many prestigious projects such as Crossrail, Libsyn and Barcelona Underground, Madrid Underground Redevelopment, and high-speed railways in Spain and Italy. He has more than 16 years of experience working in tunneling industry, and he is a very dynamic and active person, equally involved with the industry as well as academia. And he has been a wonderful mentor for me personally when I was in Spain for a month. I remember how he taught me complexities in designing the connections in tunnels in Midas GTS NX. And I remember our breakfast studios and huge lunches when we were in Madrid. And I'm pretty sure we are going to enjoy him speaking about his experiences in TBM tunneling, and he's as efficient of a professional and an experienced tunneling engineer as of a good person he is. So I will now hand over to Dr. Cosimo to take over and kindly share your experiences with us.
Okay, thank you, Sandeep. Thank you, Devika. Thank you for nice words. Today, I would like to speak about the design approaches to avoid problems during the TBM tunnels execution. The index of this webinar, of this presentation, is clearly divided into parts. The first part, mainly comparing the design, is the input data from the geological area and geotechnics, the choice of machine, the segmental design, I mean not only the joints, also the segments, the water, the tunnel portals. And then in parallel, I will show you some problems we could have mainly during the execution of the tunneling, mainly due to the problems that can very often came up during the execution of the tunnel. For example, the TBM lining defects, problems during excavation, some possible solutions. And then finally, I would like to highlight the personal risk analysis I usually do when I am involved as a principal designer. Okay. First of all, the geology. I am a doctor and civil engineer. I have a background in geotechnical and structure, but so I'm not geologist. And but geology is not only an input; it's the input. It's the most important data we can have for our design. From the geology depends the choice of machine, the ground pressure, the inflow water, all the possible problems we can have during our execution of the tunnel, during our excavation, is everything related with the geology. So in this case, we have to understand the medium we are going to excavate and also his behavior, not only at microscopic, not only from microscopic point of view, but also from microscopic, in particular, relating with the mineralogy of the soil and of the geology of the ground. This is directly related to the construction. If we want to avoid any problem during construction, we have to read very, very carefully the geological data, and we have also to be assessed, and this is very important, from very good and very expertise geologists. Everything is there, and the main thing we have to understand is how and when to implement the different geological model and different geological characterization. When, during the design, during the excavation, during the detail design, and whenever, and who should do it. If, for example, this is something I all the time I bring to in general to everyone. If in this graph I relating the number of pages we usually dedicate to each of the geological annex. If you, for example, you will have our geological information. I mean, if it is Mesozoic, Cretaceous, and whatever, you have a really high and extensive description. This is very good, but this is not what really we need in our design. Then we have the physical property of rocks. Normally, we standard like 50 page, so quite less. These are very important, cover very and play a very, very fundamental role in our analysis, because depends on what properties we are using. Then finally, we have the permeability and water levels, which is very important for tunnels, in particular if we want to choose the good machine. So in general, this is distribution in a geological appendix of number of page, and actually our job as designer or design manager or whatever should be to improve this number and to have a better description of physical properties of rock and their permeabilities. Then there is something also important because normally the geological information or the geotechnical investigation comes from someone who is not precisely the underground engineer. I mean, the man who then finally has to do the calculation and has to do the design. In particular, in some cases, you can see that we could use windows, like boreholes, like windows, I mean, to inspect and to check the distribution of different strata and to capture also the extent of this strata relating to our tunnels. So in some cases also it is important to have a word with the people who are going to do the geotechnical and the geological investigation to bring also our criteria, because then we are going to use these parameters, we are going to use these permeabilities and whatever. So it is important to be in the loop and to have a word on it. In particular, is relating the water. The water inflow for is what is really important to set up in our design, because it is not also, it's not only interesting the choice of the machine, as we can see later, but also the design of the segments. Okay, so it is very important to have a correct understanding of the inflow, or if we are going to do the watering, the process of the watering of our segment, and then when we at the long term we are going to establish the designer water table. Okay. So this is very important also to bring, and it is not. I mean, here I bring some analytical formula. The first one is the Atkinson and Mail. You will see something in bibliography, and the second is came from a very old book, The Art of Tunneling of Chesney of the 1970s. So. The other issue we have to understand is that our ground, in rock or soil or whatever, is not something. I mean, it's not something isotropic. It's not something that is its behavior is can be efficiently reproduced with the isotropic model. It's something very anisotropic. So this anisotropy can be translated in that we are parts of our tunnel where we are expecting and where we will have more water inflow respect to other parts. It is important to understand and to know from geological information where we will have these areas and how to cope with good solution. Here, for example, in this slide, I bring the solution given by Alberts and Gustafsson for the Sweden tunnel mainly built in granite with very fissured or very weak granite, where they had very vertical discontinuities, and they usually treat these discontinuities with grouted material. It is a solution. There are thousands of solutions, depending on which type of machine we can use. If we can carry out injection from the machine, or we have to use some other type of treatment. Okay. The geology. The results of all this data, the water inflow, the possible discharge, I mean the possible flow in our tunnel, where we will have these areas and whatever, has to be translated in a longitudinal profile. This longitudinal profile has to have everything. All the information has to be collected in this data, has to be clear, and everyone from the geologist till the structural engineer has to be capable to read efficiently this data, and can be very easy to implement it in different design. Okay, then maybe to be understand the real behavior of the excavation, you can carry out also a modeling or 3D or 2D or very complicated modeling. Bear in mind that modeling is a tool. All the time you have to have with you a pen and a piece of paper to carry out your hand calculation, and then comparing with your modeling. Your modeling is just a tool, but it's very powerful. And right now, with the increment of the finite element software, you can carry out very complicated 3D models, like in this case they are the portals, which is very interesting and attractive to model in 3D analysis. Okay, these are some examples of geological profile. I would say not geological, geomechanical profile, because you don't have only the geological information, you have also the geomechanical, I mean the depths of the strata, you have the influence of, you have the presence of the water, you have the parameters you have to employ, and whatever, for different cases, just to show you where I mean, how will be the your tunnel in only in one go, only in one window. This is very important to have a better understanding of what we are going to expect. These, for example, are the faults area. I'm sure that I'm not telling you nothing new, but it's important to underline that this data have to be reproduced at our best with all the information we have. Okay. Now, the first question someone has to ask is the TBM always the good choice? No. In some cases, the criteria based on the tunnel length is not valid. We have, in general, in the tunnel industry, we have the classical graph of which I didn't collect from because I did not want, because I don't like it, with the tunnel length in function of if we have to use the TBM or drill and blast or other type of methodology. This is very dangerous to use this method, because does not take into account only the length because of the economical point of view. Because if a TBM, if our length is more than 3 kilometers or 3 or 4 kilometers, the TBM results more economical from point of view, but doesn't take into account the geological conditions, the geotechnical ones, and whatever. So if geotechnical geological conditions are not favorable, maybe TBM is not a good solution, because TBM is a prototype and it is very rigid design. We cannot provide any changing in a TBM. It's very difficult to change section or change. It is not so dynamic as the new Austrian method of the drill and blast or whatever. So the idea is parallel with the economical point of view, also to develop our technical, forgetting, for instance, the economic, and concentrate on the technical issues. And depending on the RMR, personally I use the RMR, but you can use other characterization like the GSI, for example, if you are working in a fleece, or the cool button if you are working in a granite, and depending over of the possible, I put here some example. These are in Spanish, but this is where is convenient, where is rentable to use the TBM, and when is not, and which type of TBM also, if it is single shield or double shield or slurry or APB, and whatever, we will see later. Okay. Then also it's very important to carry out a SWOT matrix about the availability of our machine. Because I mean, we have to understand which are the worst situation where our machine is going to work, to have and to have a better idea of the real production of our segments. Then there is okay. Imagine, and for instance, that the TBM is the good choice. Okay, so we have to do the TBM selection, and here there are very clear criteria. The criteria is based on which type of ground we are expecting. If it's a hard rock, we have the grippers. If it's a rock, we can use, for example, the mono shield or single shield. Depending on the classification of rock, if we have a rock, very good rock, like grade 1, grade 2, or a fair rock, grade 3, we can use the single, or we can go with a slurry. In this case, the slurry is here. We can share this with between rock and soil. And then if our ground is under the water table, we do not have more option than using an APB or a slurry, or a mixed solution. The APB, how it works, the APB, the first two rocks, the hard rock and and the single shield, they don't have a possibility to push. They don't have the possibility to have a pressure on our face, so they are working mainly on. In the case of the shield, they're working mainly supporting by the backs on the segmental rings, and in case of hard rock, they are supporting by in lateral head walls of the tunnels. For the pressure APB, we have the APB where we have the ground pressure plus the water pressure, and this is balanced against the pressure of the face, which means that in the area of the face we are working in hyperbaric, so in more than atmospheric pressure. So we have a Stirling pressure, so our front is not going to have a problem of stability. The Slavi is more or less the same. The only thing is the differences between the forms and in one case of the APB or the Slavi in case of the Slavi pressure if we want to use. Okay, right now there are other TBM, for example, other manufacturers. They are studying APBs that can be work like a Slavi or like a pure APB. Okay, now. Where to employ a Slavi, where to employ an APB, depends on the permeability of soil. In particular, if our ground is quite open or granular material, we can use a Slavi without any particular problem. If our ground is more silty, more clay, and is more close or more cohesive, we should use an APB because we need to penetrate more, and so we need to mix better the ground we are going to excavate. Okay. Now here there are. I bring also some classification or some. Definition of for different manufacturers about the tunneling equipment. If because then what I mentioned is like a general rule, a general fix of thumbs, but it's not. We should also understand, depending on which manufacturer, which TBM or which APB is better for our ground. So there are some cases. I bring, for example, the Mitsubishi. I bring, for example, Kawasaki, depending on the soil models, the permeabilities, the water permeability. I mean, the water permeability here is, is meant the permeability of soil. So depending on which cases we can use a Slavi, we can use a milled plexi or mixed shield, and then we can go till from TBM to other to the face pressure to TBM. No, then I bring also the ErecNet that they are one of them that they are including also the diameter of excavation as discriminant because it's important also the diameter in the dimensions in this case are very important considering the pressure, no? Because if we have 6 meters of APB, is not the same pressure we have to apply in for example 16 meters of diameter. So also this has to be taken into account. This is another catalog for another manufacturer, depending on if we are closer, fully open, partially open, and whenever. In reality, and then I put most of manufacturers are working towards the so-called universal TBM, a machine which is capable of working under all rock or ground and hydrological conditions. Can be worked like TBM if you have a rock, then we can install our elements for putting pressure, and it can work like a Slavi, or depending over the ground we can find, it can work also like APB. There are some studies on that, in particular ErecNet and what was Lovat. Right now, Lovat is not existing. It's Caterpillar. They are working in parallel because they are competent. They are working in parallel towards this type of machines. Okay. Now, for example, this is a TBM for rock. This is the photo of TBM. This is the when the TBM was passing through an 88 TM, the nearest method tunnel, because we have to cross a very small tunnel, so we decided to bring this TBM. This is the face. This is the same face, and this is when they are dismantling the TBM. Is a view of from the back of the head. Now, if you choose a TBM, for example, and this is something is parallel on the execution. If you choose, for example, a TBM for rock and do not consider the possible water inflow, you could have problems. And during the excavation, I mean, your machine is not able to excavate the rock because they have water, so your cutters are sliding on the face. So you can push you on your backs in the jacks, but you can work because you have the pressure of water, and this pressure of water is not balanced, so your TBM can't work. Solution sometimes is the closing the so-called windows. The windows are possible to operate and to install cutters, also to inspect the front face, and whenever closing the windows, maybe you can work on it, and you can give a small pressure to TBM and capable to cutters to attack the front and to excavate. This is exactly what happens if you have water. This is the front. Is a view of this face, and you have the water here. See, you have the water here. Is a fault area, so you have a really high water. And in this case, you have to close these windows, and then you have to provide. You cannot. This is very rigid method, the TBM, so you can't do an injection of front. You can do it because you don't have a possibility to access the front. Okay. Another issue is choosing a good set of cutters to avoid problems during excavation. For example, right now, the cutters we are usually using in our TBM is 19 inches. Not all manufacturer can provide this type of rings of cutters, so we have to also study the possible abrasion, maybe with Los Angeles index or with other parallel tests on our rock, on our ground. If, for example, there are some mineralogic, like from mineralogical point of view, for example, if we have a silicium, or if we have some different elements which can produce a lot of destruction of our cutters, we have also to take it into account. No, in particular, this is the installation of cutters. As you can see here, we have a reduction of cutters. Once we install the cutters, we have to check from windows, in the case of TBM, if these cutters are in line with our face. Otherwise, we can have a problem. In particular for TBM, we can't excavate a very vertical face, and we can have problem in our pushing and in our segment. This is an example. This is a test. Once we install when we install the new cutters, we are checking that the distance is more or less the same, and we are checking that the machine is working properly. In particular, this has to be done by inspection, but also the software of the TBM. For example, if it's an ErecNet either empty, is capable of giving us this image. Okay. So this is what I was referring. So if, for example, it's normal that it has to be not perfectly vertical, but should be the most vertical possible. Otherwise, in this case, if this cutter is not cutting, the equivalent pressure of the machine will be very, very can be a really problem to our segments. Okay, and then also to the performance and the advance rate of the machine. Okay. So this is an example of a number of cutters changed with the number of rings. As you can see, once we are changing the first set, the number of the cutters is increasingly very high, and we have to control that this tendency line is more or less linear. Because then we have also to check if also we are not facing other problems. Maybe a lot of pressure on our back of rings can push too much our cutters, so our cutters can overwork, and this overworking can lead to a less life of our cutters. Then, for example, another issue we can check is the filling of the annular gap between the TBM, the BB, and our rings. In some cases, we can choose depending of the ground, of the level of the ground, and depending of the permeability of the advance, and whenever we can use, we can choose which type of TBM we can use, if it is open TBM, if it double shield, and whenever. As you can see, if the ground, expecting ground is, for example, grade 4 or less, soil in this case, a double shield, the production and the average advance rate in double shield is much more than the open TBM. No. Another option to improve our design and to take into account our design is a so-called fast sealing. The fast sealing is to have the injections line behind when we are going to fill the gap between the TBM and the excavation directly on the shield. So once we have the TBM, the TBM is advancing and our ring is on the contact with ground, we will already have our section, our completed section. This is very important to control the deformations of the segments and to avoid problems from structural point of view, but also from durability, because our ring will work better also from a water tightness point of view. Now we go to the design. Once we have chosen the machine, we go to the design. Which loads we should consider in a TBM analysis? The ground loads, the pushing from jacks to ring, the construction loads, the water load, if it's present. Not all tunnels have a water load, the earthwork, the fire, and any other load derived from particular conditions. One very important is these 2 points. Which load combination we have to use if we are fulfilling the standard requirements, Eurocode 2, maybe Eurocode 7, but we do not have a particular Eurocode for tunneling. And this is also some opening problem in European standards, but also in all world standards, because the only standard we have regarding the TBM analysis is the Japanese standards regarding the shield tunnels. And then the field condition, for example, the settlement analysis, and then the most important is the construction process. Once we decide which machine we have to use, which type of cutters, where we have our injection line, and when the injection line will work and will fill completely the annular gap, we can use and we can provide a good or reasonable good design. Okay. So we, in general, in TBM tunnels, we have 2 types of joints. The joints are the circumferential joints, which are the joints between different segments, different rings. And then we have the longitudinal joints, which are different joints between different segments, but belonging to the same ring. Okay. So the construction process normally comprises the ring installation, which is the construction loads, the joint design, and the backfill injection. So the first step is to understand when our ring, our segment is going to have and is going to receive the loads. Normally, for example, I use the ground reaction curve, or the curve of the convention of the confinement curve is I am accustomed to using it, but there are other designers who use other typology. Is okay. For example, the number of stability or the others, they are problems. So yeah, we have no problems to use. In my case, I use this one because it's the most reliable approach for circular tunnels. This also is working very, very good. So the deformation of shield is between, this is our reaction curve. We start from the geostatic, and then less by less we are coming to our front face. Front face is this is the front face of our tunnel. So the differences between delta 1 and delta 2 is the deformation due to the shield, and then from delta 2 to delta F is the final deformation, and this is what we have to collect with our ring, with our shield, and then we have to take into account in our design. Okay, this something is bringing also here. Okay, these are a lot of closed formulation to check and to calculate the delta 1, delta 2, and delta F. There are the formulation of Ribacchi, or Borghignoli, or Lombardi, Hamburg. There are thousands of them. No? Then the construction process. The first is the ring installation. So this is how we create a ring. This is a classical ring with a steel reinforced rebars. Right now, there is a new tendency of substituting the steel rebars for fibers. Fibers are very good. We have to check that during this process, the construction process, we still can have we should check also during the construction process is the pure fiber ring is working or not. These are the formula we usually apply. This is the stocking. I will go fast because you are know better than these things. This is the handling, where you are tricking with the vacuum and you are putting it in your during your tunneling, and this is the pushing, when you are pushing, so you are pushing your ring against the others, and so you are creating a pre-compression along your ring is capable of maintain and keep the circular form. The joint design. The joint design is quite more interesting because it's a pure structural element. The joint design, it ensures the connection between segments and between different rings. The geometry of the joints is a discontinuity region, so it's the region, okay? So, and it should be analyzed accordingly. And the rotation of the joint must be evaluated as directly affects the water proofing system. So we have to analyze different approach of the joints. Okay, how we can do it? Normally during the design, we can use the approach of Saraceta, or Verruit, or Gladwell, Johnson. Here I bring some of them. And this is the equivalent beam. It's basically substituting and like changing the joint area for an equivalent beam, provoking the reduction of thickness of this beam, and providing this in our numerical analysis. We will go back on it later. Okay. Then there are also some other checking we should do is the bursting and spalling effects. Here they have the classical closed formula. These are based on Leonard, so I don't have to explain to anybody to how to do it. The only thing is that if we are having the bursting and the spalling, we have to check that, for example, in our fibers, the concrete is capable of resisting the bursting and spalling effect. Normally, these are the most onerous checking for the fiber reinforced rings. Then we have the analysis of five. The five analysis normally is done with the approach of error code 2, the isotherm of 500 degrees, which is a very good approach. In particular, if our ring, as happens in say 85% of cases, is working mostly under axial load. So it can be a very easy and very quick check. The latest version of Eurocode, the consolidated one, prevents also or states that we can use also the formula based on the portals, which is also a good option. Personally, sometimes I do a transient analysis, for example, in this case in Flac, which is it's quite easier to do it in Flac than other software. So we can efficiently reproduce the design and fire curve very quick. No. In this case, these are the internal forces due to the fire loads. In this case, if this is very important, this graph, if this is the distribution of compression and tension along our ring, as you can see, is more or less constant. The implementation of fire analysis brings a lot of compression, which normally is not a problem because our structure can work in compression because it's a ring, it's a closed ring, and brings tension. This tension is most of them is really dangerous because our structure in general, our ring is not working properly during tension. No, this can lead to an increment of the bending moments, and so to do that, we should compare this with, for example, with the method of the isotherm in some cases. Also, this method is with the gradient. Right now, it's quite easy to do. If you provide a Flac, it's very easy. If you have a Midas, maybe it's easy. Yeah, it's the same more or less. Then at the end of the day, this is the what we are going to produce. We are going to send to our construction team or to our client, whenever. It's a drawing where we are going to reproduce all the things in all the rebars and the position, the quoting and the quotation and whatever. Just to understand, this drawing has to be very, very clear because it has to be read by someone who then has to build it. So it has to be clear without any doubt, without any repetition. And it is important to keep all the information in this drawing. Okay. Now, this is the ideal world. Okay. In general, in tunneling, in particular in TBM, if the choice of a machine is not properly good, or if we have problems during because we do not know the geology of the geotechnical and whatever, we can have problems in our lining. The Japanese Society of Civil Engineers in 2006 provided a category of TBM lining defects. This is this table. This table is also collected by Sugimoto, and they identify the stage, if it is the sign of construction, the category, which type of ground, tunnel, alignment, TBM, second, and whatever, the cause, but they do not identify the remediation or the mitigation measures. This depends on the site and on the tunnel. So it is not there is not one solution for one problem. Okay. So the first problem is that the first problem in TBM linings comes because we are using the equivalent beam. Okay. This model can be used once our ring is already installed and it is already working as annular, as circular form. During construction load, we cannot use this system, and it is dangerous to use this system of equivalent beam. So we have to carry out a very normal structural approach. Because if we are not fulfilling the completely our annular gap, as happens in most cases, because this annular gap is not filling in one go, it's filling in normally in 1, 2, or 3 steps. The ring we are having is this ring is possible to expand laterally, creating ovalization, and the ovalization of ring creates cracks in our ring. Normally, cracks appear at tunnel crown in this area, and then in intrados, we can see these cracks, but also we have cracks in the outer of the of the ring. Evidently, we can see it, but theoretically, the formation should bring these cracks also. How we can simulate it during our design is we can simulate like an equivalent beam, but not with but considering only the bolts like acting rebar in our analysis, and to provide here like I would say a spring, an equivalent spring which is capable of rotating. This will efficiently reproduce the distribution of the bending moment, and this distribution of bending moment in along the difference of joint section is capable of redistribute the internal pressure. Actually, we carry out in a paper, we carry out a comparison between the measure of the value on site with the values calculated in our structural assessment, and we reach more or less the same value. Another issue is that we have seen in the many design that this construction load are not taken into account, and people use the hypothesis of wood, which is the hypothesis to have a reduction of the inertia of the ring during to the presence of joints. This is good. This is a good approach. It's an analytical approach and is valid only for analytical calculation. The ground reaction curve or the convergence confinement curve is not valid for finite element analysis. The other effects or other TBM problems we can have, there are the rotations between two different joints. This rotation of joints has a structural problem because right now the stresses are not passing through the center line of our joint, are passing in area, in a small area. So we have an increment of pressure on this D region. This normally can be efficiently assessed by a student tie model, and also we could have problem of water tightness or our gasket. Then we have the same problem from the convex if we are working with a tapered ring. This can be, this we invented something to measure the ring, and we measure the angular differences and the angle between the fixed and moving part, just to have an assessment of the problem. And then we have the misalignment. As you can see, the misalignment can have the same problem of the plane joint because it's moving the introduction of our load on this D region. So normally it's assessing with the student tie. In some cases we need a reinforcement. And also, as you can see in this photo, this is a cut of a ring because we had to install here the conveyor bolt. This is a problem also for gasket because this gasket is not in contact as per design. So here we will have a problem of water tightness. And we have the ruptures of tunnel. This defect is quite common in almost all tunnels I've visited during my life, and this is the most common. And this because in particular in this area is very delicate, and during handling, in particular during handling, they can have problems of installing. So they are pushing, and when you are pushing too much, maybe you can create some local ruptures. This is normally the 100%. The bolting of segments is 100%, so it's along all the length of the ring, and only in 10% of cases this L2 is affecting the equivalent contact area. Only 10% is affecting this the area of joint. So this is not a big problem, but maybe it can be a static problem in our design. Then sometimes during the rotation of the machine, we have the so-called position 0, which is the position that the machine is doing to establish the I mean, it's 100 or 200 rings to establish the position, the normal position is called position 0. And in some cases, we can have a continuous joint affecting more than 2 rings, and this has to be evaluated from structural point of view, normally carrying out 3D models with with the joints to evaluate the distribution of the loads on this area. Normally, this has to be avoided. In some cases, however, our ring cannot resist the internal forces derived from the structural defects, and we have to reinforce our ring. Remember that the ring, and this is very, very important, the ring has built by means of compression jacks, and demolishing it is not a good idea. So if someone is telling you, I will demolish this ring, escape. Say, okay, no, it's not a good idea. So the construction process needs to be studied in detail. It's not trivial. These are means of different sections, and also this reinforcement has to be checked against the water, against the space proofing we have for our tunnel, no? Because at the end of the day, our tunnel is for something, so we have to check it very. The construction process also is very difficult in this case. I bring some video how to do it. So as you can see, you have this has to be done out of tunnel. We have here some hinges. These hinges are construction hinge valid to allow the construction and how low to install it on tunnel, and we are able to install this very, very quick. As you can see, we open, and then they are moving to the other case. This is the ones we have already put in place, and then they are pushing with an excavator because of safety and because this element is very heavy. So they are working without interaction with the man. So this also has to be assessed. Then in some cases we have to pass 2 different tunnels. Maybe they use the so-called tortoise, which is a hard fill embankment. Normally, the hard fill, I saw it many times in my life. The hard fill only states vertical reinforcement, but no mention about horizontal and longitudinal. This is a very big mistake because the hard fill must resist the horizontal. Otherwise, you can have this problem. This is the machine, and you have this problem because you have a failure of the face, because once you are installing, this is the BTSym. When you are installing when you are pushing the TBM, you don't have a horizontal pressure, so you don't. This is excavating something. This is creating a face failure, and this brings you a very, very big. Okay. The water inflow. I mentioned at the beginning that the water inflow is a very, very big problem, and can be dramatic. Can be a dramatic problem if we have, depending on the pressure of the inflow we have. We can have the case of Ayesa in Spain tunnel. It's very famous, and here we have till 400 MPa water pressure on our tunnel. This can be something like that, or can be something let's say about 10 or 20 meters of water, and you can have your tunnel ready for be used, but you can have this problem of water, so your tunnel is not fulfilling the criteria established by you, and so you have to fix it, and fixing it is very difficult and very expensive. Then it is important also to take out the water from the invert arc. In most cases, I see, for example, that during our design, we are very worried about the crown of the tunnel, but nobody is taking into account the invert arc of the TBM. The invert arc actually can have problem of heave, of uplift, depending on where is founded, and we are also to quit water from the invert arc, and because it's very can be very dangerous. Another tunnel, so you have a problem here from your invert arc. So we have perforated the invert arc, and we are putting the water inside the tunnel, and we are taking it not out of this. This you can see in white one. They are the first trial of injection behind the tunnel in order to stop the flow. As you can see, we could not reach any good results because of the water pressure and because of permeability. In this case, then we solved with another option with going different material. Portals. In general, all the tunnel design statement, whenever they assume 3 or 4 meters on top of a TBM machine, this is not needed. This is we can attack with 1 meter. It is not a problem, particularly if you have it in APB. Usually we can provide a tension slab on the top, just not to provocate any problems to the ground. So it's not a problem. These are the classical example of ground treatment of the TBM portals, which are depending on the country where we are, depending on the designer, depending on what you as a designer feel more comfortable with a type of design. This is an example of a failure of TBM. If you have a rock about designing, considering the depth direction of the strata, this is very important. I know that it's trivial, but sometimes, as you can see in this image, it's not so trivial. Also, do not treat a portal like a normal wall, because it's not a normal wall. You have to consider that you are going to excavate under the anchoring system, if you have anchoring system, and you can have detentioning of soil. So you have to consider it very detailed, and it can be a problem during as you can see in this photo, it's a problem during your execution. Personally, I prefer to assess the portals considering the TBM, considering the construction process, as I mentioned at the very beginning of this webinar, by means of 3D analysis. This is a type of something we did here in Spain. This is a tunnel. Maybe if you have a portal with a very bad conditions from ground and hydraulic point of view, it's useless to start directly with your TBM. So maybe sometimes it's better to attack with save the conventional method like New Austriac, and then once you are in a very good rock, you can bring your TBM and you can install your TBM, and you can start with the TBM in a very bigger rock, more than excavating very weak rock with the TBM and suffering it. Then finally, there is a mention to the risk analysis. Normally in Spain or UK or whenever, the risk analysis are like a table with a color table with the green, yellow, and the red, considering which risks are associated. We are identify, we are classify, and then there is a possibility of solving. In particular, what I usually do for tunneling, considering my experience on it, is to, in general, not only TBM but also in conventional, is to present very detailed risk analysis. In particular, for example, if I estimate this case, for example, if I estimate values of convergence, depending on which type of convergence, I can use different section or different segment 1, 2, or 3, and then if I have more than the established convergence, so I will start with the remediation measures, which can be ground treatment, external ground treatment, double injections, grouting, and whatever. Okay, or even reinforcement of the section. This is important for this risk analysis because we should give an answer to all the risk, and if it's possible, evaluate this risk, this answer in terms of costs and time to give the most reliable answer to our client. Our client is not only construction; is also a public client to have a better idea of what is going to happen. Finally, I would like to have the conclusion. The conclusion is, first of all, the geology is not an input, it's the input. Be careful with faults, water, and risk, and whatever. If you choose a TBM, the TBM must respond to the worst geological scenario, not the average, the worst one. The design of segments is the design of joints. So the joints has to be assessed very, very structural from structural point of view, not assessed by geotechnical engineers, but by structural engineers. Be very, very proficient in structural calculation. Defects in TBM can occur. You have to know how to solve them and give the correct answer. For this reason, it's important to have a very solid risk analysis. And the demolition of a ring is not a good option. I mean, personally, I don't suggest it. So if you find water in your tunnel, try to push all the water around the tunnel, not only in crown, because you can push out to the crown, but then it can concentrate on the invertac, and you can have failure by heave or by uplift in your invertac, so you can have problems. And then portals for TBM tunnels do not require specific cover, like for example in the conventional one, but you have to consider the pressure applied on your retaining structure, otherwise they can fail. With this, I end. Finally, you can rest, like this man close to the portal. And then finally, I bring some bibliography. If you want to study, or if you want to bring more, or if you want to read more data, you can have a look to these papers. And with this, I finish. The displacement of the faults slip. It depends. You have to depends of the excessive displacement depends on what you have, which type of machine you have. If you have a single shield, however, you have to take into account also the fault area during the segment. You have to take into account the maximum displacement. This normally has to be done with a geological modeling that give you that they represent the discontinuity of the fault area, and they give you the maximum displacement. This has to be static, or if you are in active fault, it can be also dynamic. Actually, I didn't touch the problem of earthquake here of segment because we did not have time. Okay. While launching TBM through a ramp, in case of inclined launch, web segments will primarily face adverse bending moments and minimal bending feature. They will have the maximum bending moments. This depends on or your type of facing pressure, and the pressure on the jacks normally are the first rings the rings that are suffering more and more. Depend also of your reaction structure. If you are working with a steel reaction structure, and then you are working with a steel dowels, steel segments, or we are working against normal, I would say normal concrete reaction. In general, they are the first ones, the rings that are suffering more from bending moment point of view.
So I think those are the first three questions on the chat answered. So one for the attendees, if you would like to ask your questions using the YouTube chat, please type your questions now. There's another one that's come from Rahul. Should be on the screen now.
Rock bust situation is there any method to take into the rock busting? Yes, there are several methods. There are the method of EC regarding the taking into account the rock busting. And actually, if rock busting is expected normally, for example, for a granite or for an andesite or for a very good rock under very high pressure, also the design of grippers, because we are going to use the grippers, has to be taken into account because can have dramatically problems. I remember there was mention about a tunnel in Peru. They have a rock busting during pushing, and the TBM was entrapped in it. They couldn't move the TBM. So yeah, you have to evaluate. There are several criteria. I suggest you to use the EC criteria based on the values of RMR. If the RMR, if I recall correctly, is greater than 65, and the sigma and the compressor index is more than 100 MPa, I mean the geostatic pressure, so you couldn't have problem, and your design of grippers has to take into account it. Normally, they provide like a relaxation of the pressure, not to provide busting. Yeah.
Any further questions from the floor?
How we tackle? No, I can see. I can see the and. Oh no, because
Last.
No, this is regarding the rock busting. Oh no, to take into account when you use possible rock busting, is there how you take is there when you may run into possible rock busting, excessive displacement of this is this is I mean you have if you have rock busting, you have to follow the criteria of EC. If you have any faults, you normally have to run a geological modeling done by geologists, and they will give you the maximum displacement of the ring and the maximum expected displacement. And then you have also to take into account, in this case, you should, for example, you should do your tunnels a bit more wider to take into account the possible displacement during earthwork, While answering, can roof bolt installation can help rock bust? If you have if you detect a rock bust at roof, yes. This in the case of your ring, of your segment. But the problem of rock busting can be can be highlighted also mainly during the construction process, when you are pushing your gripper, because you are installing a lateral pressure on your rock, and you can have problem of rock busting there also. So yeah, you have to analyze it in details. I told you, comparing the quality of rock with your geostatic pressure. Recommendations? No idea is provided. Yes. Thanks so much for the professional presentation. I'm just wondering whenever you may say yes while launching yes. Okay, this I answer. I can assign internal pressure in segment in soft ground. In soft ground you have internal pressure. The internal pressure you mean I mean, internal pressure is mainly due to I don't know, if you have a tunnel for water, for example, internal pressure came from your hydraulic calculation. The problem of the soft ground is that the tunnel is you have to provide a very, very sensitive design considering all the construction phases, all the construction process to make your tunnel robust and working properly. I don't know if you have more question.
If you've got any further questions, please type it in the chat.
I would like also to underline that I mean, each machine is a prototype, and so each segment also is a prototype. So be careful to reuse projects you already have done in the past in the same ground conditions, because the ground conditions maybe can be the same, but your machine and the construction of your machine may be changed because change the manufacture or the length of the whatever, and this also can be affect your dramatically your design. Okay. How you will suggest TBM tunneling in hydroelectric projects, such in case of geological prevalent? It depends. In hydropower projects, normally the tunnels are very deep, and they are in rock, on weak rock. So I would suggest, I mean, if it is a rock in a TBM, I would not. I'm not particularly fan of hard rock TBM because you can have problems, and I mean, or you are sure that you have very good rock, otherwise you can have problems. So how you rate? I would rate per linear meter, as you can usually do, and then consider the geological uncertain. I would work on the possible geological conditions. I don't know, maybe per linear meter of a TBM, and then considering an increment of cost by between 20 and 25%, not more, because otherwise your project will be not capable of capture the real problem. Okay. The ground. What is the effect of ground pressure in case of split? The effect of ground pressure is mainly to stabilize your face of your tunnel. So it's an active effect on your ground. The segmental lining, you are installing the segmental after the excavation. So you are so it's a passive is a passive system. So they are very different from this point of view. The effect of the ground pressure about in spread line and concrete is about 10 MPa, between 10 and 15 MPa, and the pressure of segmental lining depends on the pressure of the regular concrete. What is the best way to simulate beacons? Can we use the same assumption as for joints you showed? The assumptions, the joints are assuming the equivalent beam of the of wood. We can use it once we are sure that our ring is completely fulfilled and completely filled with the annular gap. If not, these assumptions and this solution cannot be taken into account. So depends on where you are using the segments. In general, if you have one ring and your ring is partially filled, the assumptions done by Gladwell or Johnson or whenever are not good. So you should do a structural checking.
I think on that note, and being mindful of the time, I think we should call it a wrap for the day. So I'd like to thank you, Cosimo, for taking out time and sharing your knowledge and experience with us. The lecture has been quite informative, especially in terms of picking stuff off from basics, and was a really thorough introductory talk. So thanks a lot. And of course, thanking you from the BTSym site. But I'll hand over to Sandeep now to add things from his side as well. Sandeep?
Thank you very much, Devik. And very thanks to Dr. Cosimo for sharing his wonderful experiences and bringing out the value from his experience from field as well. And thank you very much for everybody to be here with us to listen to Cosimo's elaborate experience. And a lot of thanks to British Tunneling Society young members to collaborate with TAIym to organize such wonderful talks. And I'm sure that such collaborations are going to diversify the talks that we are having, and we will be able to experience the problems that we have faced in various parts of the world and the solutions that have been brought out. And this was one of the example of such talks. It was really amazing, and it was wonderful to have you all today. Thank you very much.
Thank you very much for the opportunity. Okay.
Thank you, Cosimo. Bye.
Okay. Bye bye.